Hi, everybody, and welcome back. Today we're going to talk about another characteristic of distributions. In addition to our skewness, we'll talk about something called kurtosis today. Okay, so once again, a histogram shows us a distribution of data. So you have some variable, you measure that variable among a whole bunch of people, for example. It doesn't have to be people, but it can be. And then you chart that on a histogram, and it shows you the distribution or the pattern that appears in that data, how that variable shows up in those units. Okay, and generally we start off with the expectation that we'll see a bell-shaped curve to the distribution. Not always, but usually that's what we're looking for. There are some reasons that we don't see a bell-shaped distribution, and so we're reviewing the vocabulary for those things and then talking about why we see those kinds of differences in the distribution. So that's what we started last time. We talked about the skewness of a distribution, which of course refers to an asymmetry. Now today we're going to talk about something called the kurtosis of a distribution, and that generally refers to the sort of flatness of the distribution or the peakedness and sharpness of a distribution. So now we'll take a look at that. So here's a bell-shaped distribution, of course. We've seen this before. We looked at this at in the last one. It's a bell-shaped curve. Normal distribution is how we refer to that. Also sometimes a Gaussian distribution. So specifically for kurtosis, what we're looking at is this sort of part of the distribution. And the curvature up here at the peak is what we're interested in. So as you can see right here, there's a nice sort of average or medium curve to the distribution. So the kurtosis is the curvature that we see there in that distribution. Now, this is what we're usually looking for, is a sort of medium or moderate amount of kurtosis. Okay. So our normal distribution has that sort of average, kind of what Goldilocks might say is the just right amount of curvature in the distribution. But sometimes we get curvature that isn't like that. It's not medium curvature. It's sort of an overly excessive curvature or an underly excessive curvature, or not enough curvature, you might say. Yeah, so we'll now talk about those and how we refer to those and why they appear in our data. What are they indicating, for example, in our data? First, let's look at an overly curved distribution. So this is an a distribution with a too much curvature in the peak, or excessive curvature in the peak, we might say. So it's sometimes referred to as excessive positive kurtosis. You would see something like this and it says, wow, that's very curved. It has excessive positive kurtosis, meaning it's overly curved. The reason that this occurs is because there's so little variability. There's relatively little variability in the variable that you've measured. And you might see this in reality in lots of cases, depending on what it is you're measuring and the scale you're using to measure it. For example, if we take a look at body temperature of human beings, and that's what I've kind of done here. This is an estimate of what we might find. So let's say we look at maybe 1,000 people that we randomly selected in the population, and we said, what is your current body temperature right now? Well, of course, we know average body temperature is about 98.6 degrees Fahrenheit, and it turns out that you can't vary from that very far and still be healthy. And so we'd very likely see something like this, where most people are very close to 98.6. It's pretty normal also to find people up to as much as 99 degrees Fahrenheit and as low as 97 degrees Fahrenheit at any given moment, and they're perfectly healthy. Once you start to vary outside of those, you start to get ill. 99, anything above 99 is basically a fever, and anything below 97 is starting to get dangerously low, where you might be entering well, you're not quite in hypothermia, but you're starting to get ill in that way. And so then that's sort of the issue here, is that if there's a very limited number of options that you can have on the variable, it's likely that you would find a leptokurtic or a relatively leptokurtic distribution. Okay. Now, a couple of things that you could do to get beyond this, if you really need to get a normal distribution, is you can increase the options that you have in the x-axis. So for example, instead of going out to just one decimal point on Fahrenheit, maybe if I need to get a normal distribution in body temperature, but I don't want to manipulate the data, Maybe instead of measuring people with just 1 decimal point, now I start measuring people at 2 decimal points. And then if I have a very good thermometer that can pick up those subtle differences, maybe now I'd be able to spread that out a little bit more because people would vary more from each other on that variable. So for example, if I have only 1 decimal point, two people who measure at 99, we'll say a body temperature of 98.6 and 98.6, but it's 98.68 and 98.62, for example. Now instead of just cramming them together, they would spread out from each other ever so slightly. And if I do that to everybody, all 1,000 people in my sample, now it spreads out a little bit more on these sides here. So this side spreads out that way, this side spreads out that way, and I have something closer to a normal distribution. Okay, so that's a leptokurtic distribution. You might also think of leptokurtic as in you would need to leap higher to jump over the distribution, something like that. A little mnemonic device if you have some trouble remembering the vocabulary. Now let's look at the opposite, however. This is what is called a platykurtic distribution. Platykurtic, of course, coming from the word plat meaning flat. You see this in plateau as a flat mountain. So you can also think, and it also rhymes with flat, so a platykurtic distribution is a little excessively flat compared to our normal distribution. You can also refer to this as excessive negative kurtosis, meaning not enough curvature in the peak there, that peak area. Now, of course, what causes this is the opposite of a leptokurtic distribution. What we have is too much variability. In other words, the whatever it is you observed in your variable is so different from each other on average that it's getting spread out. There's a lot of noise in the distribution. What's interesting here is that noise in the distribution can cause all sorts of things. Like if I were to say, hey, what's the average in this particular variable? It's not as clear. Now, clearly it's somewhere in here, right? That you'd probably go with the peak, especially if it's symmetrical distribution. However, it's noisier. There's a lot less certainty in what that mean is because it's not a defined peak there. Okay, and so that's essentially the problem here with having a platykurtic distribution is it's harder to find out what is going on in your variable. And we might see something like this if we have a variable that has a lot of values it can be, or it might also be that we're using the wrong metric maybe. Like, for example, if I were to say, hey, what was the average lifespan of the last 6,000 people who died in the hospital? What was their lifespan? But I want it measured in minutes as opposed to their lifespan measured in years, which is what we usually do, right? If I measure it in minutes, it's just an enormous measure, right? Some people who were alive for 90 years are going to have enormous lifespans in terms of minutes, and then some people who died who were just born and then died, for example, there at the hospital would have very brief ones, and then you would have large variation in between. And so if I'm using the wrong metric on my x-axis, that might lead to this kind of platykurtic distribution. This particular example is dog size. Now, if you were to say dog size in pounds, you'd probably get a relatively normal distribution. Dogs can range roughly between 2 pounds and upwards of about 200 pounds, depending on the breed. And so if I measure in ounces, however, that's of course allowing a lot more variability because there's 16 ounces in 1 pound, so it allows for a lot more values to take place. Okay, so that's essentially what's going on, is there's too much variability. The units that you observed differ from each other more on average than in a normal distribution, and certainly in a leptokurtic distribution. All right, so that's a platykurtic distribution. Just to summarize then, what we just went over is that in addition to a skew is an asymmetry, as we talked about last time. If you missed that, go back and see that lecture. It's called the skewness of a distribution. In addition to that skewness, we're also concerned about the peakedness of a distribution. So not only is it symmetrical, but also how high is that peak, or how defined is the peak of the distribution in that particular histogram. So that is called kurtosis, as we said, and skewness has to do with the symmetry. Kurtosis has to do with the peakedness of the distribution. And again, as we said, there are lots of issues that come up when there's too little or too much kurtosis to a distribution. And so if you chart your data that you have and you're trying to do a statistical test, you may find that it's going to be inappropriate for your statistical test. The reason for that, of course, is that our statistical tests are often interested in having a good amount of variation, a sort of medium amount of variation among the people that we measured, if it is people. And they like to have a mean that actually does represent the entire distribution. And so if we don't have that in, for example, a platykurtic distribution, or there's just not enough variability in a leptokurtic distribution, we might not be accurately reflecting the population that we got that data from, or the people that we got that data from. Okay, that's all we'll talk about right now, but we'll get back to more of this soon. Thanks, and I'll see you then.